Let's now have a look at another three-dimensional polar coordinate system. This one is known as spherical polar coordinates. It's used as a coordinate system in situations where you have some kind of spherical symmetry. Crucial to this is the distance of the point concerned from the center of the coordinate system, the origin of the coordinate system. So let's imagine we have a situation, we have a black sphere here, and then let's look at points D, E, and F. Points D and E are the same distance away from the center of the sphere. Point F is further away. How do we have a coordinate system that reflects this? Well, spherical polar coordinates are based on the distance from the origin and two angles. So the distance from the origin is known as r, and then we have two angles, theta and phi. Theta measures the angle from the positive z-axis, and phi measures the angle in the xy plane. Let's see a diagram of this. So let's say we have our x, y, and z axis. We have the origin here. We have a point here. Yes, we can give the point in terms of x, y, and z, but let's imagine we want to use spherical polar coordinates. Well, one of the coordinates we will use, r, that is the distance from the origin to our point here. And then we have two angles. You can see when we take the line out to the point and we measure the angle that makes with the positive z-axis, that gives us our angle theta. Now, one analogy is if we're talking about positions on the Earth, then theta equals 0 would be the North Pole, theta equals pi over 2 would be the equator, and theta equals pi would be the South Pole. And theta is restricted to 0 to pi. So that's the angle theta. You could claim it is related to the latitude. And then we have the angle phi. In the xy plane, measured positively from the x-axis. So it's the same kind of angle that we've been dealing with in previous coordinate systems. You could consider phi to be related to longitude, and specifically to longitude going east from a reference marker, say the Greenwich meridian. So that's the three coordinates, the distance r, and the two angles, theta related to latitude and phi related to longitude. And of course, r, theta and phi are related to x, y and z. We see here x, y and z all depend on r and the angles. They're all proportional to r. Distances proportional to distances. Then we have x is r sine theta cos phi, y is r sine theta sine phi, z is r cos theta. So if we know r, theta and phi, we can easily get x, y and z. We can also work the other way. If we take the three equations, square them, add them, take the square root, r is equal to the square root of x squared plus y squared plus z squared. We can see that this is consistent with Pythagoras in 3 dimensions. Square the first two, add them, divide by the third equation, we get that tan theta is the square root of x squared plus y squared divided by z. And then divide the first two equations, tan phi is y over x. You'll notice that yes, we have tan theta and tan phi. And once more, it is extremely crucial to be able to get theta and phi in the correct quadrant? Well, if z is positive, you'll get tan theta is positive, and when you take the inverse tan, you'll get an angle in the first quadrant. And of course, you'd expect theta to be between 0 and pi over 2, that is in the first quadrant, if z is positive. Similarly, if z is negative, tan theta will be negative. The inverse tan of that will give you something in the fourth quadrant, and you'd need to add pi to get it into the second quadrant. Remember, of course, that theta exists only in the first two quadrants, going from 0, say at the North Pole, down through pi over 2 at the equator, down to pi at the South Pole. And similarly, you've got four situations here. X or Y could be both positive or negative. It's the same situation with the previous types of coordinate system. So let's see a couple of examples. Let's imagine we're given r, theta, and phi. We want to find the location of this point in x, y, z notation. That is, in rectangular Cartesian coordinates. So our r value is 3.3. Theta and phi, well, let's note, of course, they're given in radians. Theta is 2.2. That is greater than pi over 2. So our theta takes us from the North Pole that little bit past the equator. We're into the southern hemisphere. We would expect theta to give a value of z that is negative. And then we have phi is equal to 1.9. So maybe if we were to draw a diagram here, where do we expect our point to be? Well, theta is 2.2. We're going below the equator. We're going at an angle. Phi is 1.9. So phi takes us round from the positive x past pi over 2 to a point, say, near here in the xy plane. And then theta goes from the North Pole through the equator into the southern hemisphere, where z is going to be negative. So we have our angle theta here, we have our angle phi given in the xy plane here, and of course the distance out to the point, that will be our value of r here. Then of course we can use the formulae that we have. X is equal to r sine theta cos phi. So 3.3 times the sine of 2.2 times the cos of 1.9. We put the numbers in, we get minus 0.86, because remember, we've gone round a little bit past the y-axis here. X goes into the negatives. Y is equal to r sine theta sine phi. So 3.3 sine of 2.2 sine of 1.9. And again, working this out, 2.52. Y is positive. We're going back in this direction. Z is r cos theta. That is 3.3 times the cos of 2.2. It comes out to minus 1.94. And yes, we were expecting a negative value for z, as our theta was greater than pi over 2. We're going past the equator into the southern hemisphere. In this second example, we're given x, y, and z, and we're asked to find the position in spherical polar coordinates. We note here x, y, and z are all negative. So we have x, y, and z. Our point here, x is negative, y is negative, and then we go down here to our point here. So we would expect that our theta, because we're going below the equator, we'd expect our theta to be greater than pi over 2. We're going into the second quadrant. We would expect our phi, because x and y are both negative, we would expect phi to be in the third quadrant. Well, let's start with r though. We have the formulae. R is equal to the square root of x squared plus y squared plus z squared. We have that tan theta is equal to the square root of x squared plus y squared over z. And we have that tan phi is equal to y over x. So r first, square root of x squared plus y squared plus z squared. So square root of minus 1.9 squared plus minus 2.3 squared plus minus 4.1 squared. Bear in mind, those all square up to positive quantities. We add them and we find that our r, we get 5.07. That's our value of r. Then theta, tan theta, square root of x squared plus y squared over z. So the square root of minus 1.9 squared plus minus 2.3 squared divided by minus 4.1, we get here minus 0.73. And of course we remember that theta is in the second quadrant. We note, of course, that inverse tan of minus 0.73 is minus 0.63, and of course this would give us something in the fourth quadrant. So we add pi, so we get minus 0.63 plus pi, we get 2.51 radians. And this is indeed in the second quadrant. Then phi, the tan of phi is y over x, so it's minus 2.3 over minus 1.9. It gives us 1.21, and we note, of course, that phi, because x and y are both negative, phi should be in the third quadrant. Well, it turns out that the inverse tan of 1.21, that is given by 0.88. That is, of course, in the first quadrant. So let's subtract pi. to get? Well, it'll be 0.88 minus pi. So it's minus 2.26 radians, which is, of course, indeed in the third quadrant. So to summarize, our R is 5.07, our theta 2.51, as in below the equator, and then our phi here minus 2.26 in the third quadrant as we're looking from above.